Okay, we are live. Okay, I'm Doug. Welcome to Polynomials. This dog, she's here. She's going to be quiet and watch us and learn something, I hope. She's at her absolute shaggiest, and in a few minutes after I finish filming this video, she's going to the groomers. She has a date with a hairdresser. Her fur is nice when it's shaggy, but I like it the best when it's freshly mowed. Yeah, freshly mowed. Lie down. Lie down. Stay. Okay, so let's get into the math. This is Hearts. That's not math, this is Hearts. They are a soccer team from Edinburgh in the Scottish League. Cool jersey. That's it. Now I'm going to talk about the math. My voice is a little bit gravelly today, but we're all just going to have to deal with it. Because even with the odd sip of fizzy water, it's like this. It's okay, I'm not sick. It's just I strained my voice. So let's go. We're doing polynomials. Well, what's polynomials? Is it part of algebra? Yeah, kind of. Is it its own thing? Yeah, kind of. So let's get into it. Let's start with a review of distributive property. Always useful when dealing with both algebra and polynomials. So my first example. 2 times x minus 3. I know the students can handle this. We've done this quite a bit actually over the past few weeks. How do we do this? We have to multiply 2 by everything in the bracket. So we're doing 2 times x, but we're also doing 2 times negative 3. And it could be written 2 times x, little bracket showing a multiplication, minus 2 times 3. And that will give me 2 times x is 2x, of course, minus 2 times 3 is 6. There we go. So yes, I knew that students knew how to do this. We can also write it like this. 2 times x plus 2 times negative 3. This minus sign, this negative sign has to be there either way. It's sort of in a way of interpreting it. Because you can say, yeah, but I'm doing 2 times x, then I'm also doing 2, which is positive, times something else. So in your mind, you would think this makes more sense. But you can't just not have that negative sign. It has to be in there. So really, either of these is a correct way of writing it. And they both end up simplifying into the same thing. Just thought I'd point that out. Now, let's do another distributive example, and I have enough room so I won't erase. What if there's more? What if it's 2x times a bracket, and this bracket has x minus 5 in it? Okay, I'm doing 2x times x, but I'm also doing 2x times negative 5, and I can write it either way. I'm not going to write it 2 ways every time, so I prefer to say 2x times x minus 2x times 5. I guess that's my preference. And then we just have to multiply and simplify. 2x times x, of course, is 2x squared. So we're reviewing a little bit about exponents too right now. Minus 2x times 5 is minus 10x. We can do this. How am I doing for time? I'm doing great for time. I knew this was going to be a simple way to start. But I will do a couple more examples just to remind you that there can be a bit of variety while you're doing this thing. This multiplication thing keeps just coming back again and again when you're doing math. What if we have negative 3x squared? That's being multiplied by negative 2x minus 6x to the 4. Okay, so he's going crazy with the negative signs, but does that bother us? No, it doesn't. A negative times a negative is a positive. Oh, okay. And I can show this different ways. I think I'm just going to simplify it. Negative times a negative is a positive. 3 times 2 is 6. X squared times x is x cubed. Then a negative times a negative is a positive again. 3 times 6 is 18. And x squared times x to the 4 is x to the 6. When we multiply, we add the exponents. Not so bad. Interesting how all those negative signs canceled out. That's a good one. How about this? 2x times a trinomial. 3x squared plus 2x minus 7. We're we're doing the same thing. 2x is multiplied by each of these things in the contents of the bracket. 2x times 3x is 6x cubed. 2x times 2x, that's plus 4x squared. 2x times negative 7, that's going to give minus 14x. We can do this. I knew we could do this. It was just a review. Now we're going to move on to a different type of multiplication. And here is a spot where I really like to slow down a bit because it's so important. And that is the FOIL. FOIL. One of the best memory aids, best acronyms ever in math. FOIL stands for first, outside, inside, last. What am I talking about? Let's multiply two binomials. How about x plus 3 times x plus 2? Now remember the distributive property. We're multiplying this by both of the things inside the bracket. But this thing that we're starting by multiplying by also has two things inside of the bracket. Okay, how do we keep this straight? We're going to multiply this x by each of these things in the bracket, but we're also going to multiply this 3 by each of the things in the bracket. It makes sense. So let's show that. X times x, and I'll show it without simplifying yet. And then x has to be multiplied by this 2 as well. And then 3 has to be multiplied by the x. And 3 has to be multiplied by the 2 as well. Let's take stock and make sure we didn't forget something. X has to be multiplied by each of these things, and it has been. And the 3 has to be multiplied by each of these things, and it has been. Okay, I guess we can simplify. I guess it's safe now. X times x is x squared. X times 2 is 2x. 3 times x is 3x, and 3 times 2 is 6. Now we can simplify further, but first I want to point something out. There's my F, there's my O, there's my I, and there's my L. FOIL stands for first, outside, inside, last. So when I multiplied the two terms that are the first terms in the two binomials, that's the F, that's x times x, that's the first ones. Then the next one was the outside ones, and oh yeah, I did it. X times 2, they're the outside terms. And that's what I multiply next. And then I is for inside, so that's the two inside terms, the 3 and the x, that's when I did them. And finally L is for last. Last times last is the 3 times 2. So I did it in that order. And when I simplify it, and I can do it like this, the 2x and the 3x are similar terms, so we have to combine them if we want this to be fully simplified. So the x squared cannot be simplified, it can't be combined with anything. The plus 6 cannot be combined with anything, but the 2x and the 3x can be combined into a plus 5x. And that's our simplified final answer. Now, what if someone broke the rules? What if someone didn't want to use FOIL and they wanted to use FILE? First, inside, outside, last. It would still work. It's true, it would still work. So let's prove it. First, FILE. First, F is first times first. That's the x times x part. I'll just write the answer. X times x, x squared. And then I, the inside times, that's the 3 times x, which gives 3x. And then the O, the outsides, that's the x times 2, which gives me 2x. And then the last times last, 3 times 2, that gives me 6. And when I combine the similar terms, I still get x squared plus 5x plus 6. So it means FILE would work because of this property where, since we're adding the two answers, when you add 3 plus 4, you get the same thing as if you add 4 plus 3. That's why that worked, where the similar terms still combined properly. It was still correct. But I'm never going to do FILE again. I'm just pointing out that if we had done the multiplications in a different order, so long as we end up doing these 4 multiplications, and then combine our similar terms whenever we can afterwards, it's going to work. I'm even erasing the word FOIL, because we know what it means. First, outside, inside, last. So let's do some more examples. You don't do something that important and just do one example. So then we have these what if questions that I always like to ask. Let me take a quick look at the time. Okay, I'm done fine for time. So that was kind of an easy one. We had x plus 3 times x plus 2. It was all pluses. There were no minus signs in there. So let's do the what if. What if there are some minus signs involved? So what if we have x plus 4 times x minus 5? FOIL, first times first. X times x is x squared. O outside times outside. X times negative 5 is minus 5x. I for inside, f 4 times x, these are the inside terms, that gives me plus 4x, and then last 4 times negative 5, positive 4 times negative 5 gives negative 20. And then we combine our similar terms, and negative 5x plus 4x gives negative 1x, or just minus x. So x squared minus x minus 20. There's my answer. Interesting. When we did this one, that the numerical coefficient in the middle is so small, it's a negative 1, and then that third term, the constant term, is so big. But when you ask yourself, why did that happen, that's a good question to ask, because you look at the sizes of the numbers and what was positive and what was negative, and you're able to figure out why it worked out that way, and that's why it's good to do lots of examples. Let's do another one. Time to erase. So that was the first binomial had a plus, but the second one had a minus. What if it's the other way around? So I'll do x minus 6 times x plus 7. FOIL. First, x times x, that gives x squared. Outside, x times 7, that gives plus 7x. Inside, negative 6 times x, that gives minus 6x. And then last, negative 6 times positive 7 is negative 42. And then we combine our similar terms. Plus 7x minus 6x gives me a positive x this time, and then minus 42. And it happened again that I ended up with a great big number here and a pretty small number there. But we're seeing why. Because when we combine the similar terms and one of them was positive and the other one was negative, well, it ends up giving a smallish number there. The positive one was slightly bigger, so we end up with a smallish positive number as our middle term. This is the pattern that we want to see so that we aren't surprised by it, and in fact we're kind of expecting it. Let's do another one though where both of the binomials have minus signs, just to make sure that we cover everything. X minus 8 times x minus 9. Yeah, I used 8 and 9. Okay, so what have I used so far? 3 and 2, 4 and negative 5, negative 6 and positive 7, and now I have negative 8 and negative 9. So you can see what I did when I made up my examples. I just didn't want to keep on using 3s all the time or 5s all the time, so I juggled it around and trying to use all the different numbers. So that's just part of the fun, making up the examples. I find it fun. Okay, FOIL. X times x, that's first. X times x gives x squared. Outside, x times negative 9 gives negative 9x or minus 9x. Inside, negative 8 times x gives minus 8x. Both of them ended up being negative this time. And then last, negative 8 times negative 9 is positive 72. Now combining similar terms, negative 9 minus 8 is negative 17 minus 17x plus 72. So this time we ended up with kind of a biggish number in the middle. But we also have a big number over here. Well, 8 and 9 are pretty big. So 8 times 9 gives 72. But negative 9 plus negative 8 gives negative 17. I'm just looking at the patterns. And of course, when you multiply two negatives, you get a positive. But when you add two negatives, you get a negative. Again, patterns that we already understand because we've been working with positive and negative numbers for a long time now. So that's the FOIL. That's fun. I think I should do more examples though. Let's see now. I don't want to go too crazy with the wild examples, but let's try, what if the numbers are much bigger? We used all these integers between 1 and 9. Let's try some bigger numbers, just for fun. Because once you learn how to do something in math, you're working with numbers, and it shouldn't matter what type of numbers you have. So when we introduce a topic, we'll often choose 2s and 3s, nice small numbers, so that you don't get distracted by the number and you can focus on the lesson. But that what if pops into your head. But wait, will this always work? Or does it only work with these simple numbers they keep on giving us right now? So that's why we try it. How about if we have x plus 20, so a big number, but still a fairly easy one to work with, times x minus, 35. I'm going to the limits of what I can multiply in my head without making mistakes. But kind of round numbers, it shouldn't be too hard. FOIL, first times first, x times x, that's x squared. Outside, x times negative 35, that's minus 35x. Inside, 20 times x, that's plus 20x. Finally, the last times last, that's when the big numbers kind of matter in a way. 20 times negative 35. Okay, it's a positive times a negative, so I'm going to get a negative answer. And 10 times 35 is easy, that would be 350. So 20 times 35 is 2 times as big as 350, that's 700. So not too hard to do in my head. Now combining similar terms, that's also fairly easy, even though the numbers got bigger. Well, minus 35 plus 20, that's minus 15x. So that didn't really make it any harder, did it? So I guess if we tried even bigger numbers like 242 and 695, we might have to get our calculator out, especially when we do that last multiplication. But there's no surprises here. It's going to work the way the ones with the smaller numbers work. So that's not that illuminating after all. Let's try something else though. What if we're doing this and there are decimals involved? How about if we have x plus 1.4 times, x, I'll make them both plus this time, x plus 3.7. Is Doug going to want to do this in his head? Doug wants to watch out and not get something wrong and feel embarrassed after. I might grab at my calculator. But it's the FOIL. First, x times x, that's x squared. Outside, x times 3.7, well, okay, that's just 3.7x. We can handle that. This decimal isn't making things any harder. Inside, 1.4 times x, that's plus 1.4x. Finally, it's the last times the last. Where's my calculator? Yes, I could do it. I mean it. I could do it. 1.4, without the calculator, I mean 1.4 times 3.7. 5.18. Not so bad. What about fractions? Okay, we're going one with fractions. But first I need a sip of my fizzy water. That's good, that helps. Fractions. X minus a quarter times x minus 3/5. First times first, x times x, x squared. Outside times outside, x times negative 3/5 minus 3/5 x. Inside times inside, negative a quarter times x, that's minus 1/4 x. Finally, last times last, negative times negative is a positive. A quarter times 3/5, that's 3/20. Oh, that turned out to be kind of easy. Oh, but when I combine my similar terms, I'm going to have to find a common denominator. How interesting that my common denominator ended up being the same denominator I got when I multiplied. Is that a coincidence? Not really. Okay, combining similar terms. Okay, 3/5, that's 12/20. I'm slowing down and being careful. 9 times 4, 20, yes, 4 times 4, yes. So x squared minus 17/20 x plus 3/20. I did it. I think I did it correctly. If you think I made a mistake, you can say so. So all that really happened there was I slowed down a bit. And I think I always recommend students, when you're doing something and for some reason it becomes a little tricky, slow down. You slow down when there are lots of signs involved. Sign errors are so common as errors that students make partway through multiple step calculations. And then the fractions can slow people down. It shouldn't stop you. It's okay if it slows you down. The decimals can slow us down as well. So that was just fun. What other things can I do with this? I'm looking at the time. What if, here's one. Here's something fun and different and special and interesting and just fascinating. Okay, well, we'll be the judge whether it's fascinating after we see it. What if I have this? X plus 3, there's x plus 3 again, squared. Okay. How am I going to do this? Now, there are tricks to doing this. Squaring a binomial is what we're doing. And I know that there are tricks, and it's good to learn different ways of doing things, but one way of doing this is to just say, well, when I'm squaring a binomial, I'm just multiplying. It's the same as x plus 3 times x plus 3. And I can do that with the FOIL. So it's giving me x times x for the first, x squared. Outside x times 3, that's plus 3x. Inside 3 times x, that's plus 3x. Oh, and then last times last, plus 3 times plus 3, that's plus 9. Combining similar terms. Okay, so it's not very different. Well, it's just a FOIL. I turned this, which looks different, into a FOIL, which isn't very different. But what happened? Let's figure out by doing it again. How about if we have x minus 2 squared? And I do the same thing. I write it as x minus 2 times x minus 2. And I'm doing the FOIL. X times x is x squared. Outside, x times negative 2 is minus 2x. Inside, negative 2 times x, that's another minus 2x. Aha, that happened again. And then, last times last, negative 2 times negative 2 is plus 4. And we combine our similar terms. Minus 2 is minus 4x. Okay, so what happens when you square a binomial? You end up with the two terms in the middle being the same. They're the same size and they're the same sign. So the shortcut, one of the other ways of doing it, is how about I do x minus 5 squared as an example. Understanding what happens, I can say I'm going to jump ahead and figure out the answer. I'm going to get x squared. When I do my FOIL, x is multiplied by x. I'm going to get x to, so here, remember when I did the multiplication, I multiplied x times 3. It wasn't really, I multiplied this x by that 3, but I multiplied an x by a 3. So I'm going to multiply an x by a negative 5. And x times negative 5 is negative 5x. But it happens twice. Whatever is in the middle happens twice. So x times negative 5 is negative 5x, but negative 5x twice is negative 10x. And then negative 5 times negative 5 is positive 25. So what did I do? I'm going to do it again, just so that I can remember what I did. I squared the x, I multiplied these two numbers by each other and then doubled it. 6 times x is 6x, doubled is 12x. And then I squared this. And it works. So I don't have to rewrite it as a multiplication and then do the FOIL. But in the end, I really am doing the FOIL. So I'm going to erase this for now. And then I'm going to do the FOIL with this. Yeah. Okay. So that's a good what if. What if the two binomials you're multiplying are exactly the same? Well, now we know what if. That's what happens. You end up getting the two terms in the middle. the equal and in sign and in size. And you can apply this shortcut to doing it if you want. But what if they're the same number, but one's a plus and one's a minus? So I want to do one like that, or two. Let's try that. So that means what we're doing now is not squaring a binomial. X minus 9 times x plus 9. There. It looks the same in a way, but it's not. Because I can't write this as one binomial with a squared. It wouldn't make sense. When you square something, it's something times itself. And x minus 9 and x plus 9 are not the same thing. So FOIL, x times x squared, x times 9, that's plus 9x. Negative 9 times x, that's minus 9x. And negative 9 times positive 9 is negative 81. But what happened here now is that these are going to cancel when I combine the similar terms, and I get x squared minus 81. So that's not the same as this. Think about why it's not the same. It might seem really obvious. Probably is really obvious to you. Why is he talking about this so much? But I'll tell you why. Because I've seen this a lot of times. And I've seen a lot of students look at it and give this as the answer. They square the x and they get x squared, and they square the negative 9 and they get, they should have gotten positive 81. But they just look at it and they give negative 81. But what's really bad about it is they don't get the middle terms. The two middle terms are not going to cancel. These cancel because one was negative, one was positive, but these are both negative. That's wrong. This is going to give me x squared minus 9x minus another 9x plus 81. So two different things happen. The 81 ends up positive because both of my binomials have negative 9 in them. But these don't cancel each other because they're the same sign. So they won't cancel. It just doubles. So students who see that and give that, why is that happening? And that includes students who I know they're good at math and they're good at polynomials. So they're just going a little too fast and they're mistaking something for something else that looks kind of similar to it. So think about that, notice the difference. If you know the difference, you can't get tripped up by this. That's an interesting one. I'll do one more like this. This one here just ends up being another example of a squared binomial. I'll erase it. So another one like that. How about x minus 1, x plus 1? I haven't used very many ones, so let's use some ones. Okay, so it's kind of the same thing. It doesn't matter which one, whether I put the net minus first or the plus first. So x times x, that's x squared. X times 1, that's plus x. Negative 1 times x, that's minus x. Negative 1 times plus 1 is minus 1, and then these cancel, and I have x squared minus 1. There's a name for this in math. It's called the difference of squares. Difference because it's a subtraction, and squares because both of the terms are squares. X squared is a square. It's x squared. And 1 is a square. It's 1 squared. Same here. This is a difference of squares. X is a square. X squared is a square. It's x squared. And negative 81 is, well, not the negative part. 81 is a square. It's 9 squared. So there's a difference between x minus 1, x plus 1, and say x minus 1 squared, which is x minus 1 times x minus 1. Not a big difference, but it's a difference and it matters. Okay, enough of that. Where am I at? Okay, I know where I'm at. And I'm at the point where I turn this page over and move on to the second part of my lesson plan. And we're going to start factoring. We have done a lot of FOIL. We have done a lot of distributive property. We have done squared binomials. We've done a lot of binomial times the binomial stuff. What's factoring? Factoring is kind of like the opposite of what we've been doing. We multiply two binomials together and we get the answer. Factoring is when we have an expression and we're saying if this was the answer to things being multiplied together, what would those things be? It's not always binomials, but we're going to work with some trinomials, and we're going to factor them, and we're going to get binomials as their factors. I'm staying in there. I'm staying with trinomials right now. So x squared plus 7x plus 6. So it looks like an answer to one of those multiplying of two binomials that we did with the FOIL. So now we're saying, okay, well, if it was the answer to one of those, what would the question have been? It's kind of like saying every time you multiply, you get an answer which becomes the question for a division because of multiplication and division being opposites. So 10 times 12 is 120. Therefore, 120 divided by 10 has to be 12. And 120 divided by 12 has to be 10. So we get used to this when we're learning our math. We tend to learn multiplication of something and division of something, one right after the other. We tend to learn those together because they're kind of the same thing except backwards. So factoring and multiplying are kind of the opposite. They're kind of the opposite as well. So I guess I could say that factoring is a kind of dividing. If I divide this by a binomial, what other binomial would I get? I'm just going to factor it. So I'm going to say, how would this give me two binomials that would multiply to give this? And one of the keys is realizing, remember all of those examples we did where we had our first term was x in both binomials, and we always ended up doing x times x when we did the f part of FOIL, the first. X times x gives x squared. So therefore, I could multiply two binomials that look like this, and when I do the f part of the FOIL, I would get x squared. So that means that when I'm factoring this, when I see x squared there, I have to have an x and an x as my first terms, and that's kind of half of it done. Then what numbers will I put here? Now I started with one where everything's plus signs, kind of avoiding the negative signs for now. So remember when you did the last times last, you got the last term in your trinomial. So what two numbers multiply to give 6? There are not too many choices, but there are some choices. We could do 2 times 3 and get 6. We could also do 1 times 6 and get 6. So, which one should I do? There is a trick to this. I just haven't revealed the trick. I'm going to use 1 and 6. And because there are no negative signs involved, I think it should be safe to put pluses here. And I have succeeded. But I want to think about why this worked. What if I had put 2 and 3 instead? Because if I multiply this with the FOIL, I'm going to get that. X times x is x squared. And then outside, x times 6 is 6x. Inside, 1 times x is 1x. And 6x plus 1x is 7x. And then the 1 times 6 gives 6. That's fine. But what about the 2 and the 3? That wouldn't have given me the 7x. That would be my problem. So if I put a 2 and a 3 here, 2 times 3 is 6. But 2x plus 3x is not 7x. So that leads to the secret, the trick to doing this, which is you ask this question. What two numbers... Is this going to fit on the video? Yes. Multiply to give 6. And add to give 7. So you're asking this question. But of course we're asking it 6 and 7 this time because we have a 6 and a 7 this time. So we want to ask this question in a way that's more general than that, so that we can apply it to any trinomial that we're factoring instead of only to this one. Because what numbers multiply to give 6? Well, we could have had 2 and 3, And that does multiply to give 6, but it doesn't work for this second condition, which is 2 and 3 do not add to give 7. But when we tried 1 and 6, it worked for both. 1 times 6 does give 6, and 1 plus 6 does give 7. So that really works. That's complete. Let me do, I have room to write another one here. Where's my second example? I'm going to use, I'll use slightly larger numbers. X squared plus 14x plus 45. I'm still fitting. I'm not fitting very well, but we just need to see the expression, not me. X squared plus 14x plus 45, was it? Make sure I remembered it correctly. Yes. And we're going to ask this question again, but we're not going to be asking about a 6 and a 7 this time. Instead, we're going to be asking about a 45 and a 14. So now it should work. What two numbers multiply to give 45 and add to give 14? Well, what multiplies to give 45? 15 times 3 multiplies to give 45. 45 times 1 multiplies to give 45. Notice how I'm using factors. Factors. We learn them when we're in little kid math, and they just keep coming back and being useful. Factors are easy. So the factors of 45, yes, 1 and 45, 15 and 3, 9 and 5. I don't think I can think of any others. But then when we think about the second half of this question, that add to give 14, 45 and 1 do not add to give 14, 15 and 3 do not add to give 14, but 9 and 5 add to give 14. So therefore, I'm going to have, remember how we started that way? The x times x is x squared part, and I have a plus 9 and a plus 5. And they work with the question. So now I'm going to show another little trick, which is to call a standard form of a trinomial this, ax squared plus bx plus c. ABC being useful variables to use for this. The a and the b and the c are numbers, right? A is 1 here, b is 7 here, c is 6. A is 1, B is 14, C is 45. I keep on doing examples where the A is 1, that keeps on happening, and I'm going to keep on doing that. But the B and the C keep on changing to all sorts of different things, including sometimes some of them are negative. So what we can do is we can look at a trinomial like this one, and we can say A equals 1, B equals 14, this is messy, there, B equals 14, and c equals 45. So a step along the way to factoring the trinomial can be to define, wait, what's my a, what's my b, what's my c, so that I can figure out what numbers to put into this question. And that allows me to change the question. So I'm not going to say 6 or 45, I'm not going to have 7 or 14. I'm going to make the question more generic, more general, by saying c and b. They multiply to give c, and they add to give b. Now, that question can be applied to any trinomial. And we'll put it to the test by using it to figure out our factors for a bunch more trinomials, and I'm going to stop trying to only have trinomials that are full of plus signs. I'm going to start introducing some that have negative signs. This is fun. Just looking at the time. Okay. It's kind of messy, so I'm going to rewrite the ABC thing after I erase. I'm keeping that question there for a while, maybe till the end of the lesson. So way over here, I'm going to write that form. This ABC trinomial where we know the A and the B and the C are numbers. But now I'm going to write an example down. How about x squared plus x minus 6? And over here I'm going to say A equals, B equals, C equals. Well, the A is 1. A keeps on being 1. So I'm going to just leave this here. And I'm going to do my examples down in the middle. I'm going to leave this here and I'm going to leave that there. Okay, but in this case, B is 1. Well, x means 1x, and c is negative 6, okay? The negative sign matters. We have to keep it with the term, with the coefficient. I'm trying to use the right terms. All right, What two numbers multiply to give -6 and add to give 1? Okay, we have to think about the factors again. The factors of -6, very similar to the factors of 6. 1 is always the factor of every number, and itself is always the factor of every number. So I'm just going to ignore the negative and I'm going to say 6. Let's work with 6 now. So we have 1 and we have 6. And then after 1 we try 2, and yes, 2 works, it's a factor of 6, and we get 2 to multiply by a 3 to give us 6, and we're finished because 2 and 3 are right next to each other. So we've got all the factors of 6. 6 is a bit of an easy one to give the factors of. But now, because we have reached this high level of math that we're doing, and negative numbers matter, we have to admit that these are also factors of 6. So all the same numbers except with negative signs have to also be factors of 6, because -2 times -3 gives 6. -1 times -6 gives 6. And we don't only care about 6. We did this in the first place because we were dealing with -6. So when we think about -6's factors, they're the same ones. Except you're not multiplying them the same way. -2 times -3 does give 6, but -2 times -3 is not giving -6. -2 times +3 gives -6. So this is the extra little bit that we have to do. When we look at the factors of the number to figure out the answer to this question, we have to care about the negative factors as well. So what two numbers multiply to give -6 and add to give 1? Okay, so -6, we could get -6 by multiplying 1 and -6, but they're not going to add to give 1. How about 2 and -3? 2 times -3 does give -6, but they don't add to give 1, they add to give -1. We're on to something now. How about 3 and -2? So the answer to the question is 3 and -2. The only pair of factors that will work for both parts of the question are 3 and -2. 3 times -2 is -6, that's good. 3 plus -2 is +1, that's also good. We have our answer. So we can write our answer. Writing it is the easiest part, I guess. You need two binomials, so put the brackets. You're using an x and an x. And then it wasn't -3, it was 3, so I need +3. It was -2, so I need -2. And now we verify. Now with all these examples, I'm not going to list all of the factors. I'll keep the rest here for now. How do I verify? I do the FOIL. So the greatest thing about factoring, I guess, is that you can verify it yourself really quickly, because you just have to do the FOIL, and we all know how to do the FOIL. X times x is x squared, x times -2, that's -2x, 3 times x, that's +3x, 3 times -2, that's -6. Combining similar terms, -2 plus 3 is +1. Yup, worked. Okay. Now we'll do a few more, and we'll do them a bit more quickly. So I'm erasing this, I'm erasing all of this, and I'm erasing these. But I'm keeping the a equals 1 because all of my examples have a equals 1. X squared minus 5x minus 36. What two numbers multiply to give -36 and add to give -5? So this is useful. Writing this is useful, especially when you're still learning. The students who are really good at this might be going the whole thing in their head, but don't do that until you're ready. So I'm writing these. What two numbers multiply to give -36 and add to give -5? Okay. When I add the two numbers, I'm getting a negative answer. When I multiply them, I'm getting a negative answer. So this is part of the thinking. If you multiply two numbers and get a negative answer, you know one of them was negative and the other one wasn't. You know your laws of signs. So I'm looking for a negative number and a positive number. And when they add together, they're giving a negative answer. It means the negative number that I'm looking for is bigger than the positive number. Think about that. That is a pattern worth thinking about when you're learning this. Two numbers that multiply to give -36. One's positive, one's negative, and the negative one's bigger. How about -9 and +4? Is that working? -9 times 4 is -36. -9 plus 4 is -5. It's working. -9 and +4. That's what I said, right? Notice how writing the answer is the fast part. FOIL. X times x, x squared, x times 4, that's plus 4x. Negative 9 times x, that's minus 9x. Negative 9 times 4, minus 36. Combine similar terms. Yep, that's negative 5x minus 36. It worked. Keeps on working. So now I can do them faster because I have found a method that works. I am going to erase this one, all of it, and erase the b and the c, and leave that stuff. It's helpful. Next one, x squared minus 10x plus 21. We need to do a bunch of these. I'll do a lot. I think I'm going to do 12 between now and the end of the lesson. Chucking the time. I intend to do 12. We'll see if I can do 12. But the students need to do more than 12. You need that puzzle book full of these. That great big puzzle book. The annual giant hardcover puzzle book full of these. You need lots. Because doing a lot of them is what's really going to make it gel. And then you won't make mistakes later. And the thing is, this factoring thing and this squaring of binomials and multiplying two binomials that aren't squaring, all this stuff we've been talking about, it just keeps coming back. It comes back in higher levels of math, but kind of as a step. A step you need to do in a multiple step process you're learning. Oh yeah, we have to factor. Oh yeah, we have to multiply two binomials. Happens all the time. So because that keeps on happening later on in math, if you practice a lot now, you're just going to be really good at it, and you're not going to be making mistakes. And you won't want to, when you're learning that higher level of math, you won't want to be thinking, okay, how do I factor again? You don't want to focus on the lower level that you already learned. You want to focus on what you're learning now. So that's where practice is really helpful. I know I say that sort of thing a lot. Okay, what two numbers multiply to give 21 and add to give negative 10? They're multiplying to give a positive number. So they're either both positive or they're both negative. But there's no way that they're both positive because two positives would never add to give a negative number. So we see this pattern. When we have a minus here and a plus there, I need two negatives. Two negative factors of 21, like 3 and 7. Because 21 doesn't have very many factors. It has 1 and 21 and it has 3 and 7, that's it. So 3 and 7 both negative. X minus 3, x minus 7. FOIL x squared minus 7x minus 3x plus 21. It's working. X squared minus 10x plus 21. It worked. That's fun. Seeing the patterns, recognizing the patterns, which includes the signs, is fun. Oh, I never wrote my B and my C. That was lazy. Okay, I'll do it next time. I'll make sure I don't forget the next time. How about x squared minus 7x plus 6? Remember to do them. Okay, what two numbers multiply to give 6 and add to give negative 7? I need two negatives again. Two negatives will multiply to give a positive, but they'll add to give a negative. And 6 doesn't have very many factors. So it's going to be negative 2 and negative 3, or it's going to be negative 6 and negative 1. But to add to negative 7, it's the negative 6 and negative 1 that's working. FOIL x squared minus x minus 6x. Yeah, that's adding to negative 7x. And then, yes, plus 6, yes. We're good at this. And we're going to just keep on being good at it, and we're going to do some more. X squared plus 6x minus 16. You know that was going to happen. X squared plus 6x minus 16. What two numbers multiply to give minus 16 and add to give positive 6? Again, if they're multiplying to give a negative, one's positive, one's negative. And if they're adding to give a positive, the bigger one must be the positive. 16, 8 and 2. 8 and negative 2, yeah. 8 and negative 2, 8 times negative 2 is negative 16. 8 plus negative 2 is 6. This is just fun. Let's face it, that's fun. What a cool puzzle. Great puzzle book that would be. Okay, x squared minus 2x plus 8x minus 16. And one of the things I'm liking the most is that I'm not afraid to make a mistake, because I'll catch it. When you know, the student doesn't really have to multiply these with the FOIL to check, but I like doing it. Yeah. So yeah, I would catch my mistake now and be able to try again. Nearly finished all these. I want to do, there's another little topic I want to go into, and I want to leave enough time for it with my last 4 examples, but I think I'm getting close to the end here. Yeah, I only have one more from this little batch. So let's do that one, and then we'll jump ahead into something else. Something that's not very different, actually. X squared minus 2x minus 120. What two numbers multiply to give negative 120 and add to give negative 2? They're multiplying to give a negative, so one's positive, one's negative. They're adding to give a negative, so the negative one's bigger. Another thing to notice about this is they multiply to give this great big thing, the biggish numbers. But when they add, because one of them's, the negative one's bigger, the canceling that happens when you add a negative and a positive is leading to a kind of small answer. So that means these two numbers must be quite close together. And I think a lot of people at that point would say, oh, I know the answer. They'd realize 10 and 12 multiply to give 120. And 10 and 12 are really quite close together, and the difference between them is 2. So it's working. You just have to make sure of the signs. Which one's bigger? The negative one's bigger. So it's positive 10 and negative 12. Yeah. X squared minus 12x plus 10x minus 120. X squared minus 2x minus 120. Yep. I've done all the combinations I can think of about pluses and minuses and small numbers and big numbers in these positions. This is good. I still think we need more practice, but we'll get more practice, because when we move into the next topic, which is finding the roots of a trinomial like this one, we're going to do all of this over again. We're going to factor. That's how we're going to find the roots. What are the roots? I think I'm finally safe to erase my ABC stuff. I'm going to keep that question though. What are the roots? Different ways of answering that question. I'm trying to figure out how I want to answer it right now. I don't want to be distracting. Let's draw a trinomial first. X squared plus 12x plus 27. The roots are the numbers that I can replace x with that will make this equal 0. Now I could have written the equal 0 over on this side, but we know with equal signs it doesn't matter. 0 equals this trinomial means the same thing as this trinomial equals 0 would have meant. So I just happen to put the 0 on the left. But to make this equal to 0, there has to be just the right number. You can't just plug any number into x and expect it to become a 0. I'll try 1. 1 squared is 1. 12 times 1 is 12. 1 plus 12 is 13 plus 27. That's 40, not 0. Okay, so trial and error. Trial and error won't be the best way of doing this. But we know how we can test our answer. Once we find an answer, a number that should make this equal to 0, well, we'll be able to plug it in to check. So I will do that. I intend to do that. How do we do this? We factor it. We know how to factor, so what two numbers multiply to give 27 and add to give 12? 9 and 3. It's kind of an easy one. It's all pluses, so we know they're both going to be positive. And 9 times 3 is 27. 27 doesn't have that many factors to choose from. 9 times 3 multiplies to give 27, and 9 plus 3 multiplies to give 12. So this is going to be, and I keep on writing the 0 equals, x plus 9 x plus 3. Now, a thing we all know in math, which is when you multiply two things and your answer is 0, it's because one of the things you multiplied by was a 0. But you don't have to have them both be equal to 0. Like you could say 4 times 0 equals 0. That's true. 0, 0, but 4 doesn't have to be 0. It's also true that if we did 0 times 0, we'd get 0. But it doesn't have to be two zeros. It can be a 0 and anything. A 0 and anything will multiply to give 0. That was really maybe the worst bit of erasing anyone's ever tried to do. Okay, so two things multiply to give 0. One of them is 0. So how do we make one of these be equal to 0? We can say, well, if x is negative 9, negative 9 plus 9 is 0. Let's try it. Oh no, I can't just leave that as an x. I said x is negative 9, so the two x's that I'm showing here have to both represent the same number. So negative there. Negative 9 plus 9 is 0, and negative 9 plus 3 is negative 6. And 0 times negative 6, of course, is 0. So it's working. But it's not the only answer, because I was just focusing on this, saying, oh, negative 9, the opposite of 9, that'll work. But what about this? Negative 3 should also work. Let's skip over. If x is negative 3, negative 3 plus 9 times negative 3 plus 3, this doesn't give 0. This gives positive 6, but this gives 0, and 6 times 0 is 0. It's working. So what's a better way of showing that? That's a big mess. I want to show it. I show it with what I call the split. We're going to split these. You know one of them has to be equal to 0. So which one is equal to 0? We have a choice. So we can say, oh, well, if we have x plus 9 equals 0, and if we do x plus 3 equals 0. So I'm just making each of these things equal to 0. And I'm going to get two different answers. I'm just doing algebra. I'm subtracting 9 from both sides. And here I'm subtracting 3 from both sides. I'm getting the same answers that I did the other way, but this is a more efficient way of showing it, I think. So, to find the roots, roots. And this is actually root beer flavored sparkling fizzy water. Karma. Okay. So I have my answers. That's what finding the roots means. I'm running out of time. I'd like to do a couple more examples of this roots thing, so I better hurry up. Okay, we all know what we're doing. I'm going to do it this way for my next examples. So it's going to look the same. How about x squared minus 3x minus 10? But this time I'm writing equals 0 over here, just to prove that it doesn't matter whether we do trinomial equals 0 or 0 equals trinomial, it means the same thing. I'm factoring what two numbers multiply to give negative 10 and add to give negative 3. One must be negative if they multiply to give a negative answer, but the other one must be positive, and the negative one's bigger. So, what factors does 10 have? 10 and 1, which aren't going to work. 5 and 2. So the negative one's bigger, so that means the 5 is the negative one, and then the 2 is positive. FOIL. I'm not going to write it, I'm just going to think it. X times x is x squared, x times 2, that's plus 2x, negative 5 times x, that's minus 5x, plus 2x minus 5x. Yes, that combines to give negative 3x, and negative 5 times 2 is negative 10. This works. Verified. I don't know why I'm holding this thing. Not looking at it very often. Showing my algebra. Add a 5 to both sides. Showing painstakingly every step, the way I do when we first start algebra. These cancel. X equals 5. Not showing it. X is going to be equal to negative 2. I'm subtracting 2 from both sides. It cancels on this side. 0 minus 2 is negative 2. So 5 and negative 2 are my answers. And what keeps happening is that one of the answers, you could sort of see, oh, what minus 5 equals 0? 5 does. I don't really have to show this because it's easy. But I guess it's not always easy. Sometimes the numbers are really big, or maybe they could be decimals or fractions. So you have a way of showing it if you're ever finding it's tricky. Show it. But yes, I could picture students looking and saying, oh, it's going to be 5 and it's going to be negative 2. And they're right. This is good because you're showing your steps. You know how math teachers like it when students show their steps. Let's not get into math teachers and how eccentric they can be. But they're correct to be eccentric in that way. Couldn't help but say that. I really just couldn't help myself. I had to say that. X squared plus 5x minus 24 equals 0. Factoring. What two numbers multiply to give negative 24 and add to give positive 5? They are going to be positive and a negative, and the positive one's going to be bigger. 8 and 3 are factors of 24, and they're 5 apart. So it's going to be x plus 8, x minus 3. Slow down, Doug, double check it. Yeah, I'm doing the foil in my head here. So equals 0. Split. X plus 8 equals 0, so x has to be equal to negative 8. X minus 3 equals 0, so x has to be equal to positive 3. That's a 0, not a 6. Okay, I did it. One more. Oh, I went over my time. But I only have one more example on the page anyway, so I'm going to do it. This is fun. It's a good thing it's fun, because finding roots is very useful. We're going to see it again, x squared minus 10x plus 24. Hey, we got another 24. But this is not the same. So it's a different example. They both had 24, so that's all. What two numbers multiply to give 24 and add to give negative 10? They have to both be negative. To multiply to give a positive but add to give a negative, they have to be both negative. What are the factors of 24? 6 and 4 is going to be the ones. We're going to have x minus 6, x minus 4. Yep. Foil. Yep. Okay. Equals 0. Oops. Forgot to write it both times. Equals 0. Okay, split. X minus 6 equals 0. X therefore equal to 6. X minus 4 equals 0. X is therefore equal to 4. There are my roots. I finished. Kind of rushing at the end because, come here, you, come here. Did you learn something? Come on. Come on. Ugh. I don't know. I think she may have been asleep. So from me and my beautiful Shaggy assistant, who won't be Shaggy the next time we see her, I want to say thank you for putting up with me while I teach math so enthusiastically. I'm looking forward to seeing you next week. Goodbye.